recording, no problem.
All right. Oh yeah, it's there now. Meeting is now streaming live on YouTube. I can see this message.
No, it's just trying to set up.
It's there, ma'am.
Yeah,
And
yeah.
also, ma'am, start AI companion, please.
Yeah, that is automatically there, sir. I have
Yeah,
in the
it is
setting
done. Yeah, it is
itself.
done. It is done. Yes, thank you. Yes, Sapna, we can, I
Yeah.
think, start now.
Yeah, we can start now. Right. So good morning, good evening, everyone. I'm delighted to welcome you all to this special lecture series organized in celebration of the International Year of Quantum Science and Technology. A century has passed since the revolutionary discoveries that led to the development of quantum mechanics, a theory that has fundamentally changed our understanding of the natural world and has also transformed physics. This year, the Indian Association of Physics Teachers is organizing a nationwide webinar series on quantum mechanics. This seventh webinar in this series is hosted by IAPT Regional Council 23, Himachal Pradesh, and is centered around the theme Teaching Quantum Mechanics and Physics Education Research Studies, including new paradigms and emerging trends in quantum technology. We sincerely appreciate your participation in this event and look forward to your valuable engagement. On behalf of IAPT, it's my great pleasure to extend a warm greeting to all our distinguished participants. I want to start by extending a hearty welcome to Professor P.K. Ahluwalia, the National President of IAPT, whose vision and leadership have served as an inspiration to organize this webinar series. I would also like to welcome Mrs. Rekha Ghorpade, the Secretary of IAPT, whose diligent dedication and administrative skills have made this kind of event possible. Special greetings and hearty welcome to our esteemed speaker for the day, Professor Brian Lane. We are truly honored to have you with us, sir. Dr. Lane brings a vibrant blend of physics and education, focusing on preparing future science educators through innovative teaching techniques and research. So today he's going to talk on the topic highlights from investigating and improving quantum education through research. I would also like to warmly welcome Professor Vanna Luthra, a dedicated and inspiring educator in the Department of Physics at Gargi College, University of Delhi. Finally, I would like to express my heartfelt welcome to Senior Professor Ghatak, our President RC23, Dr. Kuldeep Sharma, all the dignitaries and the participants from across the country who have joined us today. On behalf of IAPT, thank you all for being here. So before we begin the proceedings, I would like to invite Professor P.K. Ahluwalia, President of IAPT, to say a few words.
Thank you, Sapna. I am delighted to have and welcome Professor Brian Lane here. I think it is our good fortune that Professor Lane is here. Professor Lane, I have gone to your YouTube channel, Let Us Code Physics. And I think that's a wonderful place to learn how to code and think about physics.
Thank you.
It's great that your innovative teaching methods called letter home labs, that is also something which is very inspiring. And I'm really looking forward to your talk today. Plus, I would also like to mention that India is having international conference on physics education this year in the month of December. And I'm sure that you will be there as our invited speaker. And we are looking forward to your presence there also. So once again, I welcome you and all the participants here, especially Professor Ghatak, who has very kindly joined us today. Thank you very much.
Thank you, sir. So let's start the session. And before that, it's my privilege to introduce the chairperson of today's session, Professor Vanna Luthra, currently serving as the Professor of Physics at Gargi College, University of Delhi. Professor Luthra's career is marked by her pioneering work in nanomaterials, gas sensing, and energy applications. She has been awarded the prestigious Boys Cast Fellowship by the Department of Science and Technology to work at University College London, UK, and the Raman Fellowship by UGC to conduct research at the State University of New York. Professor Luthra has established a modern physics research lab at Gargi College, mentoring both undergraduate and doctoral students, with 5 PhD awardees under her guidance. Her academic excellence has been recognized with numerous honors, including the Meritorious Teacher Award by the Government of Delhi and IAPT DSMA Award. She has led multiple national and international collaborations, and beyond her research, Professor Luthra is deeply committed to science outreach, active learning, and teacher training, having mentored over 300 undergraduate educators nationwide. Her contributions span invited talks, keynote addresses, training in computational physics, astronomy, and climate change education. She is also a prolific author with over 38 international journal publications, book chapters, and educational resources to her credit. So please join me in welcoming Professor Vanna Luthra. Over to you, ma'am, and
Thank you.
can start the
Thanks a
session.
lot. Yeah, thank you so much for your kind introduction. And it is my good evening to all the August gathering of the physicist, Professor Lane and Professor Ghatak. Professor Ghatak's presence also makes this meeting all the more important. And thanks to Professor Aluwalia ji, our president, and Professor Rekha Gorpade for this meaningful initiative, because this is the need of the hour. And the efforts of Professor Kuldeep Sharma, Dr. Sapna, yourself, and all the team members of RC23 are praiseworthy. This webinar series on quantum mechanics education and per series is crucially important, as it provides a linkage between the effective pedagogies and strategies for the quantum science education and ongoing celebrations of the International Year of Quantum Science and Technologies, which we are celebrating IYQ 2025. I am pleased and honored to introduce speaker of today, Professor Brian Lane. He's working as an assistant professor in University of North Florida. His area of expertise are computational thinking, physics education research, science communication, and teaching of physics. His education is in the PhD in physics from the University of Florida in 2008, and his dissertation is on conductances in the two impurity Anderson model. I'm happy to read his biography, which says that he has been enjoying physics since his high school days, and he has been a physics at Jacksonville University for 13 years after completing his PhD, and he has incorporated computation into every physics course which I think he was teaching or was a part of. And he has been an invited speaker, workshop host, and committee chair through American Association of Physics Teachers, that is AAPT, and he enjoys working on STEM education tabletop role-playing games. His affiliation has been with American Association of Physics Teachers, member and former chair of Committee on Physics in Undergraduate Education, Partnership for the Integration of Computation into Undergraduate Physics Webinar Planning Committee, and an article reviewer. He has been on the advisory board of WJCT community and an Infinite Master Pathfinder role-playing game. He has been granted numerous grants and contracts such as NEF STEM Physics Tech Network of worth $93,000 to support physics teacher education or preparation, and including many others on environment and computer integration and AI integration into the classroom. And he has numerous presentations and publications on physics education research, specifying and emphasizing the use of drawing, simulation, visualizations, games for improving classroom experiences for the students, and I am sure for the teachers as well, for the topics like potential energy, X-ray diffraction, exam writing through a problem grid, and he has edited one focused collection in investigating and improving quantum education through research, and which is a topic for today as well. Today's talk will shed light on investigating and improving quantum science education through research. And we all are eagerly waiting for your talk, and I'm sure that this is going to inspire many more those who are present here, and it is being live streamed, so it will be a resource for future also. So welcome to you, and we invite you to deliver the talk. Thank you so much.
Well, thank you all so much for that lengthy introduction. I have very little else to say about myself, so let me just go ahead and start sharing my slides here. So this is a presentation I delivered back in March at our American Physical Society Global Physics Summit in part to celebrate the International Year of Quantum, and I found it was helpful for folks in the audience to complete this survey that I'm sending to you in the chat. Because I don't know everyone's backgrounds. I would love to customize this presentation for everyone's backgrounds and interests. So if you don't mind just taking a couple minutes, I've put the link there in the Zoom chat so that you can tell me about who you are, your familiarity with physics education research or quantum education, what you're interested in, and I'll use that to customize the content that we share today. If you have trouble getting to the link there, there's also a QR code here on the screen that will also take you to that same survey, just 2 questions. While I wait for folks to fill that out, let me tell you a little bit of my version of my story. So as was mentioned, my PhD dissertation was on theoretical/computational condensed matter physics. I enjoyed my time in condensed matter. I learned a lot. I really feel like that shaped my identity as a physicist. But one of the things I noticed as I was going through grad school was I really didn't get a good idea in my undergraduate study of what life was actually like as a physicist. So I thought when I graduated college that when you went to grad school and got a PhD, you learned how to solve every physics problem there was, and you learned how to tackle anything and how to answer every question. And then I got there, and after about a month, our quantum professor, who later became my PhD supervisor, said, "Well, that's all the exactly solvable problems in quantum mechanics. The next semester and a half is spent on approximation techniques." And I really felt like the earth fell out from under me because no one had signaled that to me as an undergraduate, that as physicists, we really live with a lot of uncertainty, and we really live in a world of approximations and trying to get everything back to the harmonic oscillator. And so after finishing my PhD in condensed matter, I switched to physics education research in part because I want to help students gain more authentic physics experiences, specifically in quantum mechanics, where so much physics research happens that we don't necessarily share a lot of at that first couple years while students are learning what physics is like. And so I use my experiences in condensed matter and computational research to inform my perspective on student learning and to help me think through, if I want to improve the physics learning experience for students, what kinds of things do I need to prioritize? What kind of cultural or practical lessons do I need to signal early on so that they have an idea of what life is like as a physicist? So I'm going to go check on the survey results in just a second, but I also want to make sure everyone has access to these slides. So this is an interactive slide deck that I invite everyone to open. I see I have a please make presentation. Oh yeah, give me 1 second. I needed to get my link over here. So here are the links to the slides themselves. Oops, I think if I press enter. No, I need to press Control Enter. There we go. So if you want to also open the presentation slides, those will also open for you automatically after you complete that 2-question survey. So let me tab over there for just a second to see what our responses are like. So I first asked folks, which of the following best describe you? You can select as many as you like. We've got about half the room has a background in physics education research. Wonderful. We've got a couple of folks who are at least familiar with PER, but then we've got a few folks who are not familiar with PER work. Okay, so that's very good to know. We've got about a third of the room is teaching quantum mechanics soon. So great, wonderful timing for this presentation today. or we're involved or interested in quantum education for high school. Wonderful. Yes, I'm here for another presentation. Like I said, I originally wrote this for a conference back in March, so some of these questions might not be 100% applicable. One of you saw that I was presenting. Wonderful. So nice to see you. I did at the March session, one of my grad school classmates whom I had not seen in probably about 10 years was in the audience. And so he clicked that one. I was so delighted to see him. All right, so what are we interested in? Oh, we've got pretty evenly distributed bars here. Let's see, what's our top two? Our top two, we would love to get an overview of quantum education, and we'd love to help learners make sense of quantum concepts. Wonderful. So you might have noticed that on the survey there were those emojis over on the questions that you responded to. Those are not just there for decoration. Let me get to this slide and then we'll turn on the full screen. There we go. That should be sharing the full screen. Yes, it is. Great. So those emojis that you answered are also a sort of index for this presentation. So on any one of these slides, which again, I invite you to open from the chat, you can navigate to the things you're interested in. So we were primarily interested in an overview. So we're going to particularly look for the teacher raising her hand here. And we were interested in helping students make sense of quantum concepts. So as I go through the slides, I'm going to make sure to spend a good amount of time on the items that relate to an overview and that relate to making sense of quantum concepts. Now, of course, that bar graph was pretty evenly distributed. So as we're going through this, if I start to talk about an article from this focus collection that's not as interesting to you, feel free to skip ahead to look at something that's more of interest to you. And of course, please do bookmark these slides. They'll be available after our session today. You can feel free to go through and review things, click on the links. Everything is hyperlinked to the article that it discusses. So let me give you an overview of the focus collection we're here to talk about. So this is a focus collection we released in Physical Review Physics Education Research. I was honored to collaborate on this focus collection with my fellow guest editors Marisa Michelini and Chandralekha Singh. We also had a wonderful advisory board that sort of took the main load of reviewing articles, giving us feedback on topics. I do want to say very much thank you to these folks. As was mentioned earlier, this focus collection was motivated by the International Year of Quantum and this need for us to prepare students for these careers in the second quantum revolution, where quantum mechanics, it's going back to my roots, it's not just for condensed matter anymore, right? So we're approaching a point in history where we want general students, like any STEM student, to have a little bit of familiarity with quantum, the same way we want them to have a little bit of familiarity with classical mechanics. And we're all around the globe kind of figuring out how best to do that. A little bit of timeline for this focus collection. In December of 2023, we published the invitation for proposals. We were hoping to get a good set. Previous focus collections have received on the order of 30 to 40 proposals. We received 52, so a very popular topic, high demand, lots of great research going on. And so within a month, we had received 52 proposals. We went through a review process on those proposals. We gave feedback to the authors. I do want to give a big applause, honor to our authors who had to turn these articles around in pretty short time because we needed their full manuscripts by July 2024. By that point, we had received 29 articles, so some of them decided that their article is better off in another venue or that they needed more time, but we received 29 articles to review. And as of April 17th, the final of 24 articles were published. These are all available open access on the Physical Review Physics Education Research webpage. They're all on a nice collection page for the Quantum Focus collection. And on April 21st, my fellow editors and I published a summative editorial as sort of a set of guidelines for what's in these articles. If you're teaching this particular class and you want to think about this topic, what kind of articles might you go to? So think of this presentation as a complement to that editorial. So if you listen to this presentation and then go read the editorial, the goal is for you to have a good idea of what's in the collection so you have an idea of what you want to focus on reading. I also want to give a thank you to the funding sources for these articles. The majority of these articles were externally funded, either by agencies or by their home institutions. And of course, more than half of those funded are currently under threat due to the funding cuts going on here in the United States. So I do want to just highlight that and thank these folks for working through those challenging times with us. Okay, so we had a number of folks who would like to see an overview of what is going on here in quantum education. But first, there are some folks here who don't have a physics education research background. So let me just take a couple minutes to give my perspective on what is PER. What do we mean when we say we're a physics education research person as opposed to an education research person? So the first thing we do in PER is we identify a learning challenge. Certainly there are plenty in quantum mechanics, right? I dare say nobody in this room has an easy time learning quantum mechanics. Nobody on the planet has an easy time learning quantum mechanics. Once we've identified a learning challenge, we try to consider a framework. And framework is just our word for the current state of knowledge on that issue. So maybe I think through a question about what resources do students draw on when they're learning quantum mechanics? And I think about the resources framework. Or maybe I think about when students are learning quantum in a group and collaborating with each other and asking each other questions and developing a set of practices, I might use the communities of practice framework. So if you think about it in parallel to physics, this is like the theory behind running an experiment. Well, then, like physicists, we take data, we administer an assessment. Maybe that's a pre and post conceptual inventory, like the force concept inventory. Maybe that's an interview. Maybe it's asking students to solve problems and talk out loud about their thinking process. And then we perform some sort of intervention. Maybe it's a new activity. Maybe it's a new way of teaching the course or a new experiment or bringing in an external speaker to the class. And then we re-administer that assessment and we try to look for differences. We look for some sort of delta, maybe quantitative, maybe qualitative, but we want to get an idea of what kind of effect did our assessment have. And probably at that point, we identify new challenges and go back and repeat. If the work is never really done, we just try to do it better than we did last year. And at some point in that cycle, not always immediately, not everything in this collection is immediately applicable to the classroom, but at some point in this research, we recommend practices to physics educators in the classroom so that they don't have to go and collect that data themselves. We can say, hey, it seems like students seem to think this way, and if you can present your material in a way that aligns with that, the students will actually learn better. And in my mind, this is very parallel to what we do in physics in general. So thinking back on my days as a condensed matter physicist, I would identify some sort of physical behavior. Hey, there's a phase transition out there. I want to go see what that phase transition does. We consider an established theory, right? Maybe there's a model I want to use. Maybe there's a maybe there's some sort of phase diagram that I want to reference. There's something I already know about what is going on there. Then we go and take measurements, right? Maybe it's in a lab, maybe it's with a computer simulation like I worked with, but we go and take measurements to go expand our knowledge. And we keep taking for measurements, we look for some crucial difference, and just like in PER, we probably identify a new behavior and try to go repeat it. And then again, we keep repeating this, and at some point, we make a recommendation to engineers, material scientists, folks building something out of this. And so I like to think that PER is to physics teaching what physics is to engineering. So just keep that in mind as you go and look through these articles. Some of these are very heavily steeped in, the sort of microscopic what's going on in the student's mind, and some are at the classroom level ready to be deployed. But it's all useful. It all eventually leads to some sort of physics or some sort of educational application. Okay, so what were sort of the big ideas in this focus collection? Well, we have a review article in this collection, just like in condensed matter or high energy physics and PER. Every couple of years, we'll get a review article on a topic. So this was empirical insights into the effects of research-based teaching strategies in quantum education. So specifically looking at when I go and transform my quantum class, what seemed to be the outcomes. So this group reviewed 50 quantum educational activities published just between 2017 and 2024. There was a previous review article in, I want to say 2015, 2016, and so this is sort of a successor to that earlier one. They found that the studies were mostly quantitative, so they are doing the sort of difficult work of measuring what students learned and what impact their interventions had. They do have a mix of undergraduate contexts and K through 12 with a breadth of topics, as you can see here. A good number were in sort of traditional quantum mechanics, some folks more on quantum optics or on experiments. We've got a few that focused on quantum computing. We'll come back to quantum computing a little bit later. A good number had a very strong mathematical focus, obviously, particularly at the university context. And then a few had these special approaches, too specific to list here on the graph. They also had 18 from the United States, 17 from Europe, so a decent balance. Most of these articles were based on groups out of the US, so there is a little bit of US focus in this collection, but certainly trying to represent outside the US as well. The studies measured a breadth of variables, mostly focusing on conceptual skills. It seemed like in a lot of this, they're not necessarily focused on the technical, mathematical, can I carry out the normalization integral correctly, but rather the concept of why do I need to normalize a wave function, that sort of base level understanding that really guides the students through the mathematical processes. They also, in this article, summarize the effectiveness of digital tools like PhET simulations or GeoGebra. They sort of on the high level, they found that in high school settings, quantum mechanics learning difficulties can be countered with this sort of demathematization, again, focusing on that conceptual piece, visualization, and innovative social methods. And then in the undergraduate context, they found that they could achieve concrete improvements in the mathematical formalism. So focusing on the concepts does not have to cost us the mathematical technical rigor there. Okay, so we have some folks who are scheduled to teach quantum mechanics soon. Let's take a little look at this section here. So it might be interesting to look at what is being taught in quantum mechanics. When I go to set up my quantum mechanics course, or when I think about the curriculum revision process, what do we mean when we say we're teaching a quantum mechanics class? So this group conducted an overview of 99 institutions. 99 institutions, just looking at their syllabi and their course descriptions. Some of these probably pretty obvious. They're nearly all teaching the Schrödinger equation and making their way to 3D quantum mechanics. And then as we get farther to the right, there's more specialized topics. So it doesn't seem like a whole lot of groups are teaching path integrals or Ehrenfest theorem. So if you're looking at your quantum syllabus for your upcoming semester, this is a good lay of the land to see what are other institutions focusing on. They also took a look at whether each course took a position first approach or a spins first approach. And I've got more information on this on the next slide. But this is a question of what you start with in your quantum mechanics course. Position first approach is what most physics majors experience in a Griffiths type textbook, where you go in, the first page shows you the Schrödinger equation, introduces the wave function, capital Psi, as a function of position and time. You start solving the Schrödinger equation, you probably do separation of variables, and you work through all those canonical problems. There's an alternative starting point, which I have used in my quantum teaching that I've been personally very happy with, called the spins first approach, that says you can technically teach all the main concepts of quantum mechanics with a spin 1/2 system. And so it actually introduces Dirac notation first and then builds up to the wave function as another representation for the state. And what they found was that about 3/4 of these institution surveys are starting with the traditional position first, but we do see about a quarter starting with spins first. So spins first, the relatively newer one, does seem to be gaining some popularity there. This is a more formal outline of the spins first approach. Typically, you start with the Stern-Gerlach experiment as an experimental basis for why we're thinking about spin 1/2 systems and why we need Dirac notation. This approach usually emphasizes the translation between representations. So you might notice here they don't tell you that the SC matrix equals, or excuse me, that the SC operator equals this matrix. They tell you that SC operator dot equals this matrix, which they use to mean is represented by. And that's their way of emphasizing there are multiple ways to represent this. This is the way you do it in this formalism. This approach makes frequent use of projection operators and builds up to the uncertainty principle and introduces time evolution all before the students ever have to see a differential equation that they are going to have to solve by separation of variables or ladder operators or all that heavy mathematical baggage that trips up a lot of students in the position first approach. One group investigated what impact does this approach have? So they surveyed 10 institutions, 6 using spins first, 4 using positions-based wave function first. And they did this really cool grouping task where they would say, select all the expressions that represent a wave function. And so they would look at, okay, a student sees a ket here with E2. Maybe they drag that in. Now that's a stationary state. Chandralekha Singh would like me to make sure to mention that that is a stationary state, not the full wave function. So maybe that's an appropriate thing to put in the wave function box. Maybe not. Psi of x, psi ket. Certainly more looking like a wave function there. Psi of x definitely looking like a wave function. Bra E1, is that on the same footing as ket E2? Maybe the students drag that in, maybe they don't. Then they see a psi here, maybe they drag it in, but this one's being integrated. So this is now giving us a scalar, not a wave function. So just trying to get an idea of what students associate with the wave function. And the way to read this graph, this is the percent of students or the fraction of students who associated each of these with the wave function. Basically, if the bars have a darker shading, it means there was a higher significant difference between the students who experience spins first and the students who experience wave functions first. And probably not surprising, but what they found was that the spins first students more strongly connected bras and kets to vectors, while the wave function first students more strongly connected bras and kets to wave functions. Now, it's important to point out neither tendency is better, right? It just shows that this different emphasis in the curriculum, what you start with, does have an impact, it seems, on how the students think about these quantities and their symbols. And so what we as educators should do is identify which emphasis is better for our context, right? Maybe we've got students had to do a particular research path that will more heavily feature one over the other, and we want to use that to choose what we emphasize. Similar study here. This same group used a Think Aloud interview protocol. For those unfamiliar, Think Aloud is literally you give the student an activity to do and you ask them to explain their thinking out loud as they complete the task. They wanted to look at basically how students interpreted these sort of symbolic forms, right? So here we have these templates of things you might see in quantum mechanics. They use what's called a card sort and expression construction. I'll let you read more about the methodology in the paper there. But again, what they found is that the spins first approach seems to have helped students navigate the two representations between the Dirac and the function type notation. And they gave some recommendations for supporting how students construct these expressions to calculate probabilities. Let's see. This is a cool article, but I think I'm nearly halfway through my time, so I think we'll continue on to. Oh, here's a good one for folks to think about as you approach your next quantum class. So this was a study on helping students learn quantum mechanics through peer discussions. So we mentioned active learning earlier in the in the introduction. And so what this group did was they used a group test procedure. Basically, first there's an individual round where the students are given an individual test. They're given about 10 to 15 minutes to complete it. So don't imagine your hour and a half long final exam at the end of the semester. Think of it more like a conceptual or check-in quiz that you might give students to just quickly get an idea of what their current level of understanding is. They would then take a few minutes to form the students into group and then distribute the group test where the students would retake the same problem, but now they've got to discuss their answers there in a group. Of course, you need longer for that because everybody's got to have that time to talk to each other. They would then collect those tests and give them a group evaluation form. What they found was that there was more knowledge construction in the large groups, meaning in terms of what knowledge folks were able to sort of develop between the individual round and the end of the group round, seemed to go better in a group of about 4 to 6 than in groups of about 2 to 3. I don't know what standards are like in y'all's classrooms, but we kind of live by, yeah, groups of 2 or 3 usually do better. This seems to suggest it works a little bit differently when it's the quantum context here. They also found that knowledge construction tended to go better in mixed gender groups rather than in same gender groups, and in groups that had a disagreement in how the questions should be answered in the individual round. And so if maybe it's a multiple choice and you've got a group of students, the group of students that answered A, B, and C is going to generate more knowledge than the students who all answered B, for example. One thing that was interesting, though, the knowledge construction seemed pretty consistent across the problem type. So whether it was an explanation or more mathematical in nature, whether it was describing an experiment or something a little more abstract, they seem to generate the same level of knowledge construction regardless of the problem type. So that's pretty encouraging there. Let's see. Another big deal in quantum, of course, is navigating the notation. So this is a paper from one of my fellow co-editors, Chandralekha. The goal in this study was to help improve students' ability to translate between the different representations in quantum mechanics. Specifically, the Dirac notation, like we talked about before, and then wave functions as a function of position space or momentum space, right? This transition often trips students up a lot. So they developed this guided inquiry-based learning sequence that's available for free over on Phizport. And so this is an example of the type of translation they were looking at, would be translating from the column vector representation to the wave function as a function of position. And so the way they did this was they had students make a graph of this inner product of a position eigenstate with the wave function here, which gets you a set of discrete points. Then they had the students connect those with a smooth curve, which is of course how you get the wave function representation. And this is the type of thing, so this is part of, going back to my interest in PER and quantum education. This is the type of thing we were never explicitly taught as undergrads, right? That physicists kind of learn to do in the back of their minds, that this is the way it maps on. But unless you have an explicit activity that scaffolds that process, you're not going to necessarily have students develop that on their own. Let's see. I don't know how much time we want to have for question and answer at the end here, but let's talk really briefly about preparing students for quantum computing. So this is another one of these guided inquiry-based learning sequences on getting students oriented to quantum computing with an emphasis on contrasting it with classical computing. For those of you new to PER, this paper used what's called the normalized gain statistic. So this is just a statistic that basically looks at what a student's score changed by in relation to how much it could have changed by. So it's useful to think of a couple of extreme examples. If my student comes into my class and gets a 95% on their incoming knowledge assessment, they've only got 5% to go. They just need to pick up 5% more on that test, and then they've learned everything they could possibly learn in a course. Whereas if a student comes in, very extreme example, if a student comes in at 5%, For them to gain another 5% is not that big a gain because they still had 90 more percent they could have gone. So a student gaining 5% could mean something very different based on the student's incoming knowledge. So this is just a fraction of their end of semester score minus their beginning of semester score divided by the maximum score they could get minus their beginning of semester score. So it's just a way of normalizing that, that amount of gain that you could get. And so in terms of what they were trying to accomplish with this tutorial, they wanted students to identify possible states for a 2-bit or 2-qubit system. They wanted to identify the students to identify examples of what could be used as a bit or could be used as a qubit. They worked on identifying the number of possible states in those systems, identifying examples of superposition states and entangled states, to describe the role and action of quantum gates, and then relate all of that to Bras and Ket so that they could calculate some outer products. All right, I see we are at about 20 minutes left for our session. I should probably check in. How much time do we want for discussion at the end of this?
Professor Brian, you can continue. We still have time, 15 to 20 minutes. You can continue. It's interesting.
Perfect. Want to make sure nobody was waving at me in the background. All right. I'm going to exit out of here for just a second because I want to make sure we focus on the stuff that folks were interested in. Do we have anybody else complete the survey? We had a few folks complete the survey. Yeah, still definitely a focus on making sense of quantum concepts. So let's see, where else do I have that symbol here? Oh, okay. This is a great one. I really enjoyed reading this article. Yeah, so as the editor for this, I just got to read quantum articles for a year and a half and shuffle them back and forth between the authors and the reviewers. This was wonderful to get to read about. So another major deal in quantum education is connecting theory to experiment. Because I'm sure we've all experienced this as undergrads, that the higher you get in the physics education, the bigger the gap is between the theory and experiment, right? The problems you can solve and the situations you can create in the laboratory. So this group created a multiple choice question sequence to help students think through, if I were to do this experiment, what would the results look like and what theory would accompany it? So the goal here was to, for example, differentiate between an operator acting on a state and the measurement of an observable, to look at how the postulates of quantum mechanics are related to quantum measurement, right? The whole idea of state collapse. Looking at the time development of the quantum state after the measurement of an observable. I remember doing that problem one time in grad school, and I kind of have to go back to that one example every time. And then to identify the possible outcomes and the corresponding probability densities of measuring position immediately after or a long time after a measurement of energy. So looking at those incompatible observables. Here's a great example from the paper. And again, this is available, their actual tutorial is available on Phys-Port. So here they give a particular 1D infinite square well, with a wave function that looks like a standard setup out of a Griffiths type problem. You measure the position of the particle and obtain x0. So there's our x0 there. Choose all the following statements that are correct. So it's things like, will the wave function instantaneously collapse to a delta function? Or will it remain as a delta function a long time after the position measurement? Or will the wave function evolve from a delta function so that it has different shapes a long time after the position measurement? And then the students are selecting which of each of them are true. So in those combinations. So that's really kind of helping students think through this as a process, and not just these individual events that are described in the postulates. All right, what else should we look at for our last couple of examples here? Do we have folks? I think we had folks interested in quantum education for high school. Why don't we chat about what this looks like for our friends over in the high school context. So this is where I do need to give the context. Quantum topics are being integrated in the high school context very differently in different regions of the world. In the United States, it's not a very common thing to see. I was actually reviewing my state's, Florida's state standards for physics, and I was surprised to see the photoelectric effect on the standards because that was not a thing when I was a high school student in Florida. It looks like we're starting to get a little bit of that, maybe more at the modern physics type level rather than the full-fledged quantum mechanics. In Europe, on the other hand, in a lot of countries, it's considered like a standard part of the curriculum. And we're trying to look at, well, how do we teach this to high school students who obviously have not had complex variables and partial differential equations? So one group here looked at making sure that quantum content is designed in a way that that is culturally relevant in the concepts that it teaches. It's an iterative outreach program to guide secondary students in the conceptual understanding of specifically quantum technologies, emphasizing quantum technology's broader cultural significance, and focusing on how it interacts with students' worldview and basic ways of reasoning. So when we talk about quantum in the high school, we're not talking about, I want these students to be able to crank out solutions to the Schrodinger equation. We are talking about helping them think through quantum on a reasoning level. Another group looked at students' attitudes toward quantum information science and technology. And so they had a 25-hour summer program for U.S. high school students. They made sure it was aligned with our next generation science standards. That's our big multi-state set of standards for science classes. Basically, if you want to do anything with high school science in the United States, you need it to align with next generation science standards. And they gave a survey of attitudes toward quantum information science and technology. And they found that this program that they ran showed some promise in how it could promote positive student attitudes toward quantum. Again, not focusing on making sure students get all of the calculations correct, but just signaling to them, you might work with some of this quantum stuff someday. Are you interested in working with some of this quantum stuff someday? Do you think it sounds interesting? Do you think it sounds challenging? Do you think it sounds approachable? That's what we mean when we talk about these attitudes toward a subject. There's also, of course, the need for high school teacher professional development, right? If we're talking about adding something to the curriculum, it means we need to help the teachers get oriented to this, both in terms of the content and how to teach it. So this group conducted 12 hours of workshops over the course of 4 weeks. They found it essential to have an interdisciplinary team. So they included a physics education researcher, but they also had a quantum theorist and a quantum experimentalist, getting the teachers directly connected to the folks who work with this, again, so that they can give the students an idea of, well, if you go into a quantum career, here's the type of things that you do. They developed this teacher self-efficacy in quantum information science and technology scale. And I should mention, anytime one of these articles gives one of these surveys, they usually invite you to go and use it in your own programs. If you do any work with high school teachers, this is a great survey to give them. They found these 3 what we call latent constructs, meaning these are the 3 main things that the survey is able to measure. It was specifically about self-efficacy. So self-efficacy is a little bit different than self-confidence. So confidence is kind of your general disposition toward, I can do anything I try, or I can do anything if I just work at it. Self-efficacy is more specifically, you identify a particular task, right? So let's use a quantum example, normalizing a wave function. And you evaluate your ability to carry out the necessary steps to complete that task. So, okay, I know that involves setting up an integral, taking a complex conjugate, multiplying those 2 functions, checking to make sure it's real, setting it equal to 1, and then solving for the normalization constant, maybe introducing a phase factor back in if I need to. Yeah, I feel pretty good about each of those steps. Maybe I have high self-efficacy on that. So anyway, they found that it was important for the teachers to have self-efficacy in these 3 areas. Their knowledge about quantum academic pathways and careers, again, always looking at what is the general education student going to do with this. Quantum pedagogical fluency in STEM integration, meaning how do I actually deliver this? How do I connect it to the rest of the science that my students are learning? And then, of course, facilitating quantum learning in the classroom. They found that the teacher participants showed significant gains overall. Thumbs up to that. For those unfamiliar with PER, the smaller this p-value is, the more significant the results were. You want a p-value as close to 1 as you can get. With what we call medium to large effect sizes, meaning does seem to be a noticeable difference, probably worth repeating. And again, the paper discusses the curriculum planning process and how to align it with the relevant standards. One of the most interesting ones to me, again, as someone who really struggled with this idea of we do things differently in physics than I expected, these two papers look at integrating Dirac notation in high school, which when I first heard that, I said, are you sure about this? But really what they look at is, again, kind of going back to that idea of spins first, where the actual mathematical mechanics that you're doing with the bras and kets is never really that mathematically burdensome, right? When you come in learning the wave function first, you're always trying to map it back onto the differential equation. But one of the beauties of Dirac notation is that it is self-contained. You can do the linear algebra, orthogonal product type stuff without really having to map it back onto there. And those are procedures and steps you can teach to high school students. And so this first group found that teaching quantum physics mathematically at the high school level is indeed possible. They found that it helped them to include quantitative problem solving, because again, obviously we're not going to have high school students doing separation of variables. And they found that it did help connect to a deeper understanding of quantum concepts. Again, the math is a tool in this class to get you to the conceptual understanding so that you're sort of oriented cognitively to what's going on in quantum later on. And they did find that the Dirac notation promoted a better understanding of quantum technology. Of course, anytime we talk about quantum computing, quantum experiments, we're usually denoting it with Dirac notation, right? And so it kind of helps them speak the language for those applications. The second paper used a reduced Dirac notation. So they've got some examples over here of how they sort of reduced some of the, I don't want to say complexity because they're still complex numbers, some of the complicatedness of it, just to make it a little more accessible. They found it was generally well accepted by the high school students, right? There's always this fear of, yeah, but my students don't want to learn another math thing. Well, the students seem to accept it pretty well. A few difficulties they ran into. So if you tried this out, there's just a list of things to keep an eye out for, is that the students tended to think of the phase angle, right? So that phase difference between two wave functions. They tended to interpret that as a deflection angle in the experiment, right? So they were confusing what angles meant in those two contexts. They also tended to think of superposition as two simultaneous states rather than a sort of collective state. And they did have a little trouble using the linear combinations of states, right? So that big idea in linear algebra of, you take your states, you add them together with certain weights. They struggled with that concept there. This next group looked at how students sort of frame the process of learning quantum mechanics. So when we say framing, we just mean your assumptions about what's going on in the room. And so in this example, they reviewed video recordings of classes and conducted interviews with groups of high school students. And they identified these three framing clusters about sort of how students operated within the context of learning quantum mechanics. So first was a call on authority. So this, for example, was to say, well, the professor told me that position and momentum are incompatible observables, so they are incompatible observables. That doesn't mean they know what incompatible or observable means or what it means when you put the two words together. They're just saying, this is the rule, this is the thing that I have learned. That knowledge is a collection of facts, formulas, and methods that aren't necessarily connected to other things. The second framing cluster was experiential. So this, for example, is thinking about how do I justify those based on what I've done in class. So maybe they've done some observations, maybe they've simulated the Stern-Gerlach experiment. And so in this framing, learning is connected to prior experience with either experiments, maybe you're showing some data, but there's some grounding for it, right? So it's getting a little bit away from that call on authority. The last one, evidence-based sense-making, is where scientific knowledge is really tentative and we're kind of constantly restructuring our knowledge based on new information that we receive. And so we're not just looking back to experiments, we're looking to the holistic patterns in those experiments to continue to refine our understanding. Probably not a surprise, but it turned out that operating in that third frame, the evidence-based sense making, turned out to be the most effective when they had to integrate their knowledge together, especially when it came to abstract concepts. So this probably looks very similar to our experiences, right? We're probably all thinking of interactions we've had with students that look like these three. We're probably thinking of our own experiences where we kind of made the transition from one to another in our own education. But it is nice to see the data where this type of thing is backed up. Last one I'll show you here. There was a survey about pseudoscientific beliefs in quantum physics. Right, despite how much research we've done on quantum, this is the type of stuff out there that is not going away on the internet anytime soon. So they conducted a survey of students and teachers from high schools across Italy. They examined what's called conspiracy ideation, science denial, pseudoscientific beliefs, trust in science, and the consumption of science content, particularly with respect to quantum physics. And so they're just looking, okay, when folks subscribe to either quantum consciousness or quantum healing crystals and that type of stuff, what else is going on with their quantum intake? And they found that for students, the lower the pseudoscientific beliefs, they tended to have better literacy in quantum physics, better consumption of scientific content, and better trust in public institutions. It was a little bit different for the teachers, that the teachers with lower pseudoscientific beliefs tended to have a degree in physics or engineering, higher quantum literacy, and higher confidence in their own ability to teach quantum and seeing value in having quantum taught to their students. I forgot to take out this. This was from the previous conference I gave this at, but I do have links there if you want to go check out other names, other articles for items related to these practices of quantum outreach. So with that, it looks like we got a couple minutes to go. So I do want to say thank you all for the invitation. Thank you for your time and participation on the survey. Like I mentioned, I'll get the link to the slides back in the chat one more time. Feel free to use this as a reference document. And please absolutely go check out the Focus collection. I do want to say thank you to our authors and our reviewers who did an absolutely wonderful job giving us incredible content to include in this collection. And with that, I'll say again, thank you very much. I appreciate y'all's time. Let me get this in the chat one more time. There we go.
Okay, thank you, Professor Lai, for a wonderful talk.
Am I audible?
Yeah, Vandana ma'am, you are audible.
Yeah. Thank you so much, Professor Lane, for giving us an overview of PER and then talking to us about different strategies and basically effective pedagogies, which are basically being tested or being administered over different age groups and by different teachers. Different surveys are also being generated in that regard. So in that respect, I think we are going to have a collection of these survey available to physicists in India also, and we can always think of collaborations with that. Different approaches may have different local effects also. So there can be some studies that things which are there from the American perspectives, how these are different in Indian context, and how to integrate from quantum education to quantum technologies, because that is the challenge which everyone is facing. So one question from my side I would like to start with: at what age, according to you, a particular quantum concept should be introduced to the students? Is there any recommended age? Is there any survey or any study which has been done in this regard?
That is a great question. I am not aware of a systematic investigation about, what's the best age to introduce. But again, I think it also varies on what your level of, formalism or rigor that you're expecting. So I have two kids aged 7 and 8. Our favorite book to read to them growing up was Quantum Physics for Babies. And when they were 1 year old, we were reading to them, this is a ball. The ball has energy, but this electron cannot have zero energy. And the goal is to, in a few pages, build up to the photoelectric effect. And my kids loved it. I don't know how much they understood about it, but it's pitched in such a way that, a 3 or 4 year old who grows up understanding that at least has an idea growing up there's something different about the way the world works at this atomic, subatomic scale. And so again, I think it depends on the learning objectives you have, but I absolutely think we can scale that probably surprisingly well.
Can there be a sequence of topics which can be prescribed according to the age in this context?
Very likely. So going back to the high school example, Dirac notation for all of its, having to learn the symbolism of the vertical bar and the angle bar and the angle bar this way. It's linear algebra. And I remember learning linear algebra in 11th grade, I think it was, just a year before graduating. And those are procedures you can teach probably earlier than that, maybe as early as the middle grade level. And so again, I think you can probably, I think what you could probably do would be identify, what math are they already learning? And then at what level can we teach each of these quantum concepts using that math or using the visual representations? I saw another, not in this collection, but there was an article about basically solving the Schrodinger equation graphically, where if potential energy is greater than the total energy, you need an exponential decay. Otherwise, you need a sine wave, but you make the sine wave different based on how big the gap is. And you can draw a solution. You're not doing any math with it. I'm sorry, you're not doing any quantitative math with it. You're not normalizing it, but you're seeing the same type of information you would see if you solved it in Wolfram Alpha. So there are certainly ways of fine tuning the math so that it's approachable to students.
You so much. Yeah,
Thank
I
you.
think there is always a chance of collaboration with you, and I am talking on behalf of all our physicists who are attending this talk today. So I think those who are interested can also approach to you, and in that case, on similar things, there can be some kind of collaboration also. And the house is
Absolutely.
open for questions. Thank you so much. Yes, Professor Aluwalia ji, please.
Please. So thank you very much, Brian. I think we were waiting for this lecture to come to India to be very specific about it. For the last almost 1 year, there has been a lot of talk in the physics community around IAPT, Indian Association of Physics Teachers, that should not we take quantum mechanics to high schools. And I think your talk has further strengthened that idea that yes, we must make an effort to move in that direction. This was one thing which I wanted to say, and thank you very much for that. Secondly, I think your lecture also very nicely provided an answer to a kind of a dilemma that what kind of approach will be the best one. Wave functions really scare away the people the way they start seeing it and doing the things. But this Dirac's notation has a very intuitive, what you can call a way of bringing things in which you just write 1 and 2 within those Dirac brackets and start understanding the things. And there is a direct relationship of that with matrix mechanics also, which I think high school students can very easily handle. That is one advantage which we see. There was one other question which was coming to my mind was, has anybody studied any kind of, say, method? We had Professor Chandalekha Singh's, lecture also, where she talks about those block qubits and how to make use of those in the classroom.
Yes.
And you also, were referring to in your talk that maybe we can try to make use of comics, etc., or something like that to, bring those concepts in front. Has anybody tried some kind of a doodling for making these kinds of concepts available to the students? Do you have any
Yes.
idea about that?
Yes, so I just a couple nights ago returned from our summer American Association of Physics Teachers conference. Hello from everybody at that conference. And we had a similar focus on quantum there because obviously International Year of Quantum, everybody wants to make sure we're, applying an appropriate focus there. One of the plenary speakers pointed out, going from this sort of first quantum revolution to second quantum revolution, there is a difference in how they emphasize notations or representations. And they specifically mentioned the Bloch sphere as something that is needed more in quantum 2.0 than was needed in quantum 1.0. When I was going through undergrad and grad school, I think we drew the Bloch sphere twice and said, oh yeah, this is kind of useful. It helps you think about, what the spin is doing and how the phases operate. Okay, great, let's move on. But really, when you get to qubits, the Bloch sphere is one of the best ways to represent a qubit and is one of the best ways to model it and kind of get out different understandings of what's going on. There's even a group that does, I think it's out of Oregon State, that does this whole body exercise where you point your arm along a complex plane. So if you want a real number, you do this. If you want a fully imaginary number, you do this, and then you can adjust your phase angle. And then you can start rotating around for a Bloch sphere. You can have two students doing this to show a superposition of states. And it's like you mentioned, it's representations we weren't all raised on pedagogically. In fact, the first time I taught using the spins first approach, I had to really reteach myself what spin 1/2 was and how it worked because it was always an add-on to the wave function. And now it is its own thing. It's presented as first thing. And I thought, well, how am I supposed to teach them the uncertainty principle with this? Well, you go and you actually work out the products that you need with the operators and everything. And it was different. It was a learning experience for me as well.
Okay. Thank you very much. And I think there is one more hand raised. Ma'am, Vandana, please.
Yes, sir. Thank you so much. And now I can ask Dr. Indulekha to kindly unmute and ask the question.
Yeah, hello. Thank you for a very nice talk. Considering you are talking about linear algebra and the requirement to know it for comprehending some of these things. And we talked about the differences between Europe and America with respect to how early quantum ideas are introduced. Is there any difference in the mathematics syllabi between the two regions? And how in setting up the physics syllabus and the mathematics syllabus and say the statistics syllabus, if something is introduced, is there some coordination between the groups of teachers setting up these syllabi so that they dovetail with respect to what needs to be taught?
Yeah. That is a great question. So certainly another big push right now is for us to integrate our STEM classes. Because a student who learns linear algebra can do so much in physics and engineering, and even their chemical reaction equations are now solvable with a different technique. And so certainly at we're seeing a lot at the introductory level, right? When students first enroll in university, we're seeing a lot of initiatives to have a physics professor and a math professor and an engineering professor in the same room teaching an integrated course where we're going to learn what a derivative is. All right, how do we use a derivative in physics? How do we use a derivative in engineering? Now let's go design something on the engineering side so that they're not necessarily having to repeat all that over and over again, and also so that the students are seeing, yes, you are going to use this across the curriculum. I don't know whether anyone's done that yet between the math background and quantum mechanics, because certainly you could see doing something similar with, say, linear algebra, complex analysis, differential equations, right? You open the first page of Griffiths, and there is this equation that has all three of those, and oh, by the way, we use it to calculate probability and statistics. The way I would love to do it, and I've never been in a position where I could, the way I would love to do it if I were teaching a quantum course, I would make the prerequisite take one of those 4 math courses Doesn't matter which one, just take one of the four, and then group students so that they had a complete set of math courses within the group. So you've got your statistics person, your complex variables person, your differential equations person, and just let them kind of build that knowledge together. I would love to see somebody try that out sometime. But as far as coordinating with folks in mathematics, I know in the US, linear algebra, and I'll put that in quotes because I want to specify what I mean by that in a minute. My experience was we had a couple weeks of that in 10th or 11th grade. You could probably do it a little bit earlier, I would think. I don't know what's typical in European high school context. Also, when I said linear algebra there, I mean we were multiplying matrices. I don't think we did eigenvalues and eigenvectors, but that's one more step. And honestly, quantum is not a bad place to introduce eigenvalues because it's important there, right? You can't do quantum mechanics without it. And it seems like it's one of those highly theoretical math things that maybe is better introduced with a physical context rather than just as a mathematical principle on its own. That would certainly be worth looking at.
Yeah, thank you so much.
Thank you very
Any
much.
Can
other?
I ask one?
Yeah,
I
sure.
mean,
Please.
just came into my mind, Professor Brian. I just want to ask you, in your view, which instructional strategies in PER has shown most effectiveness in improving conceptual understanding of quantum mechanics? Any idea or any suggestion you can give?
Yeah, there's sort of this, and we're actually trying to come out of this right now. There's sort of this consensus. Well, anything beyond lecture helps. Like anything you try, even if it's your first time, even if you feel like
That's
you're
right.
bungling it, it's usually better than just writing the Schrödinger equation on the board 100 times. So just getting that out there, anything is an improvement. We are starting to move into an era of, okay, it's time to compare teaching strategies, right? It's time to compare modeling instruction versus studio versus IEL. And those, I'm using those words specifically to indicate, we mostly investigate this at the introductory level because that's where we lose students. That's where we have the most students. That's where we want to, focus on it. But we do need to focus on these upper division courses as well. So some things that come to mind. Chandralekha Singh's tutorials certainly seem effective. Having the students kind of work through strategically scaffolded problems certainly does seem to help because it's helping the students think like an expert. I mentioned the arm motion, Argand diagrams. Anything that kind of embodies it is certainly helpful. A common theme seems to be like breaking it down to where the actual mathematical steps that the students are doing are not individually that complicated. So I remember we did one activity at a faculty workshop where we had to make a grid of dots and then we had to draw a vector with kind of randomized coordinates. Okay, that's fine. Then we had to label each of those dots by the dot product of the vector with that dot's position. We're all like, this is kind of tedious. Like this is very basic numerical math stuff. And they said, okay, now connect the dots that have the same dot product value. I'm like, okay, whatever. So we connect them. Oh, we just made a bunch of lines that are parallel to each other and all perpendicular to that initial vector. And they said, okay, this is the difference between position space and k vector space. Because when you talk about a k vector, we talk about that momentum space, you're talking about planes that are parallel. And suddenly it became a high-level esoteric quantum thing that a lot of us, myself included, had trouble understanding as undergrads. But because we did it in almost this thing that almost felt like going back to high school or middle school type of drawing and connecting the dots, suddenly unveiled what the physical significance of this mathematical thing was. And I don't, to your question, I don't know that I can put a single term on that type of thing, but it really does seem like kind of helping the students break it down and arrive at that conclusion seems to be the thing that helps a lot.
Thank you, Juan.
Thank you so much. And we have Dr. B and Meera. I may ask Dr. Meera to unmute and ask the question.
Yeah, can you hear me? Vandana?
Yes.
Yeah, you're audible.
Yeah.
Yes.
Good morning, Professor Brian. I'm Dr. Meera. from Department of Physics, Bangalore University. I have taught quantum mechanics at the master's level for a couple of years, almost a decade. I personally find this as the biggest challenge. There is a paradigm shift when you go from the classical world to the quantum world. And that is what Professor Ahluwalia also mentioned, the tendency to see things. I think the tendency to see the wave function, that becomes the biggest impediment to make the transition from the classical to the quantum world. I think what we can probably sort of align students is to see the mathematics, not really see the physical concepts that are associated in quantum mechanics. Look at how the wave function looks in different conditions. And the mathematics in the Schrödinger formalism is a little more detailed than the formalism itself. In the Dirac formalism, it's neat, it's crisp. Whereas in the Schrödinger formalism, the math is a little more involved, which means that they have to learn to deal with clean mathematics.
Right.
So I would like your input on that, the impediment in seeing things and the clean mathematics.
Oh, absolutely. Visualization so important in quantum. We talk about the wave function is evolving. Well, what does that mean? This is not the way other scientists use the word evolve for. So that does make me think of this one paper we have in the collection on, related to what you're talking about, differences in this use of the word uncertainty between classical experiments and quantum experiments, right? Because this is a great example of what you're talking about, where the students for years have learned to talk about the uncertainty in their measurement. And they think about, well, I have a ruler, I put the ruler up here, and there's an uncertainty in how I read the lines. Oh, I could get a better ruler, and I would have lower uncertainty. But when we talk about uncertainty in quantum mechanics, again, like you mentioned, there's this paradigm shift where, no, we're not talking about getting better equipment. We're talking about something fundamentally different about the universe, where that electron doesn't have a well-defined position. And so this was an interactive sort of experiment homework where they simulate a Stern-Gerlach type experiment where you can do three things. You can modify the quantum state, you can improve your experimental setup, or you can collect more data. And they asked the students, what is that going to do? Again, getting back to visualization. What is that going to do to your results? Because obviously each of those will make the results better, but better in what way? Because this part about modifying the quantum state is a different outcome than just taking more data or taking better data. And they did find it was successful in helping students distinguish between those types of uncertainty. So absolutely, helping students zero in on those differences between quantum and classical, super important. I often tell my students, if you get to the end of a unit in quantum and you say, oh yeah, this makes sense, or this is exactly the way it works in the world, go back because you probably missed something, because that paradigm shift does take some work and does take some time.
Yes. Thank you.
Thank you.
Thanks a lot, Dr. Lane, for your enlightening remarks. I would like to also add here one thing, that we need to rewrite or revisit whatsoever mathematics or computer science books we have, also in the physics. Like, for example, block sphere can be seamlessly integrated when we are teaching quantum, basically complex variables, or we are teaching the Euler's formula, or when we are talking about the transformation from Cartesian to the spherical polar coordinates, because we have to introduce that r theta phi concept to them. So I think there is a need also to rewrite or reintroduce these things into the ongoing curriculum also, so that it is not taught in isolation, it becomes integrated with what we are teaching. So that, I think, strategy would also be helpful in this regard. So with that, I'm not able to see any other question. If in case there is any remark or any other suggestion or any query by anyone, can raise hand, or otherwise I may thank Professor Lane and hand over to Dr. Sapna for the rest of the proceedings. Thank you so much. And I think it was such a enlightening talk. I think it has given thought for the future, say, per projects also, because whatsoever the deliberations are going on, I'm sure there may be many more such take-ups on those particular topics, and it may lead to more, I think, in-depth studies into this. Thank you so much for your gracious presence here. And we invite you to be in India sometime, and it will be a pleasure to meet you in person. And with that, I hand over to Dr. Sharma for rest of the proceedings. Thank you very much.
Thank you, Dr. Vanna. Professor Aluwalia has raised his hand. Sir, you want to say something?
Yeah. Professor Brian, I just wanted to bring to your attention a big exercise which we have done in the last almost 6 months in IEPT, Indian Association of Physics Teachers. And that is, we conducted a mega quantum quiz of about 22 episodes. And the last episode was today itself.
Nice.
And as we were speaking, it was parallelly going on.
Okay.
We have got a lot of, when we tried to cover whole of quantum mechanics, but we were not focusing on very quantitative things in that. It was, a bit of knowledge, a bit of personalities, bit of, throwing the, names of the concepts and trying to see whether they have heard about that or not. And we have got huge data which has come out of that. We had a very mixed kind of a group. We allowed school teachers, school students, college teachers, university students, university teachers. Anybody could have come in that. And there are very interesting things which are emerging from that also. Maybe we would like to really work on that and try to target NPR, our understanding which has emerged from there. I think we had around 450 questions in that. But we were not very, what you call mathematical in any sense. But we were interested in, seeing whether people have heard about, say, quantum computing, quantum computers, who are the pioneers in all those things. And after every quiz, what we also did was we once again created a small booklet of those questions. We didn't really solve anything in that, but it was to give a feeling to the participants that they have got something in their hand so that they can revise it and search for it on their own when they go back. So this we have done, and I think we will be in touch with you about the outcomes of that.
Wonderful.
So,
I would love to see those. If you want an external set of eyes on any kind of manuscript, do let me know.
Sure. Thank you very, very much. Thanks.
So thank you, Professor Brian Lane, for such a wonderful talk. And finally, I would like to invite our RC23's president, Professor Kuldeep Kumar Sharma, to present a vote of thanks.
Thank you, ma'am. Good evening to all of you. On behalf of IEPT RC23, I would like to thank you all for joining us this important lecture 4 of teaching quantum mechanics and PER studies on highlights from investigating and improving quantum education through research by eminent physicist Professor Brian Lane, University of North Florida, as a part of celebrating International Year of Quantum Science and Technology, IYQ-2025. Our heartfelt thanks to Professor Brian Lane for delivering very informative and enlightening talk today. We are really honored to listen you, sir, particularly throwing light on how we can learn quantum in peer discussions, navigating quantum notations, how students can be prepared for quantum computing area, connecting quantum theory and experiment, and most important, designing quantum for high school and how we can teach students at high school level Dirac notations. That is very important, because in quantum mechanics, a student always find it difficult to digest the concept of the wave function itself first. So you have given a very nice picture on this. I would also like to extend our heartfelt thanks to Professor P.K. Alwalia, National President IAPT, Professor Rekha Gorpade Madam, General Secretary IAPT, Professor Bandana Luthra, Professor Sapna Sharma for arranging this nice proceeding of this lecture today. And I am also very thankful to all respected teachers, IAPT members, and dear students for joining us this evening. I hope you all might have enjoyed this important lecture and hope you all uh, uh, going to join us in coming lectures also, which will be part of this monthly series. Once again, I would like to thank you all. Thank you. Namaskar. Thank you.
So thank you very much. Thank you everyone for joining us today. And with this, we say goodbye, Professor Brian Lane. Have a nice day. And thank you very much, everyone.
Have a nice evening.
Thank you.
Yeah.
Thank you.
Thank you. Thank you. Thank you, Vandana ma'am. Thank you.
Thank you. Thanks a lot to everyone. Thanks.
Yeah. Thanks, everyone. So now just we are closing this meet.